So this is our last unit in calculus, you guys. We're going to spend the rest of the month of March on it. And it's really just three main topics. The first one is what we're doing for the next few days called net change. Net change. Topic 2 is area between two curves. So we've learned how to find area under one curve, but what about if you have two curves and you want to find the area between them? And then the third topic we'll look at is volume. You can actually use integrals to find volumes of three-dimensional shapes as well. So we're doing a lot of integrals in this unit. And since in this unit I want to focus more on the concepts less than on the tedious math work, we're going to be using calculators pretty much this entire chapter. Now that doesn't mean that, you know, you'll only ever see a problem like these we're using calculator, obviously, right? The only reason I'm doing this is time. Really, these could be asked. Like every problem we're doing today, you could do it by hand. I just don't. It's way too time consuming. And I don't want to focus on the nitty-gritty details of integrals as much as I want to focus on these other ideas that we're developing. So if you don't have a calculator, you might want to grab one for today's lesson. All right, guys. So the topic for the next few days is something called net change. We're going to look at problems like we just did today, but a little bit more calculus-y rather than just, you know, geometry oriented. So we're going to be doing problems like that today. We're also going to look at more in-depth problems tomorrow as well. And then after that, we'll talk about these things called particle problems, and those are very common AP questions. But they're all net change questions, is what they are. Yes.
So we only have a lesson 4.
No. There's 4 for the first topic, 4 for the next part. So it could potentially go up to 12. It depends. I would like to cut them short if I can. So 4 was my overestimate. But we'll see how it works out.
I see.
Must be increasing with a.
Right.
I couldn't do it fast enough. I didn't think about it. All right. So let's do this. All right. This is printed for you. So what we're looking at there, guys, is just the first fundamental theorem of calculus, right? There's nothing special there. But in the context of a word problem, all these pieces gain some meaning to them. Okay, so let's understand that. Now, what we just saw in the last little exercise we did, the opening activity, was we integrated what kind of a function? Okay, on the opening activity? It was the speed function, right? Okay, it was a rate function. So if you integrate a rate function, what did that give us? The distance. Okay, so here we're integrating a derivative. Now, isn't a derivative just an instantaneous rate of change?
Yeah.
Right? So we have it. We're integrating an instantaneous rate of change, right, from on some time interval. Okay, so this piece here represents the rate, the f prime, and the x and the a represent the starting time and the ending time. All right, and what that gave us was how much distance the car traveled. But I'm gonna change it. I'm gonna change the wording on that a little bit. It told us how much the distance changed. It went from 0 to 230. Does that make sense? So the distance of the car changed by 230. We call that net change. So in other words, if you integrate a rate function, it gives you the net change. But the net change of what? You do need to look at the units. So once again, we're thinking of all this in terms of a word problem now. So f prime is the rate of change of f, right? Okay, so that means the change in f over the change in time, right? how much f changes over time. And dt, isn't that just delta t? How much time has gone by? And we're, in a sense, multiplying these, right? So what we end up with is delta f. Now, going back to our word problem to kind of bring this down to earth a little bit for you, we were talking about speed, which is distance over time, right? dt is time, and what we ended up with was time or distance. And that, so basically, if you integrate a rate, you find how much that numerator unit changes over time. Okay? So it's all about interpreting what we already know in the context of a word problem. Now, a lot of times, what we want to do is, this represents our starting amount, right? If you plug in A, this represents where you started at. So where did our car start at in terms of distance? 0. And this gives us our final place. So where did our car end up at the end? 230. And if you subtract the start from the end, you get the total, right? The net change. Okay, well, a lot of times we want the final amount, right? So a lot of times they will write the function like this instead. And you guys see the difference?
You just add
Yeah.
of A.
Yeah, you just add this piece over here so that what you want is already solved for. But now notice that when you write it like that, it's written like a function now. It's written like an integral function, right? F of x is equal to f of a plus this little integral function. Okay? So now in the context of our story problem, if you know the rate of change of a car, you know how long it's driving for, and you know where it started at, you should be able to find out where it lands. Okay? All right, but now I like to use cars because it's something that we're all familiar with, but it doesn't have to always be distance and time. Okay, so I'm going to give you guys a few word problems where the units are different. So paying attention to the units is kind of important for today. So let's go ahead and take a look at an example problem. All right, a chemical flows into a storage tank at a rate of h of t equals 180 plus 3t. Now, liters per minute. What that means is at 0, if I were to plug in 0 here, for instance, that means the rate would be 180 liters per minute. That's how fast it's going in at first. If I were to plug in 1, now the water would be coming in, the chemical would be coming in faster. It would be coming in at 183 liters per minute. So the rate's constantly changing. We have a changing rate, right? But we know that we have a function for its rate. Where t is the time in minutes, and it looks like time is going from 0 to 60, it says find the amount of chemical that flows into the tank during the first 20 minutes. Okay? So it's asking us to find the net change. Okay? How do you find the net change? How much chemical, in other words, flowed into the tank over that time period? Is you integrate the rate. Now my rate is h of t, right? Now they're asking for us to find out how much it, how the rate changed over what time period. So t is defined from 0 to 60, but they want us to find just how much flowed in after 20 minutes. So we're going from 0 to 20. So basically you have this chemical flowing into a tank, and it's flowing in there faster and faster and faster every minute. Okay? And our goal is how much will be in there after 20 minutes. That's what we're answering. And the way you do it is you integrate the rate from 0 to 20. So from here we're going to use our calculator. Here we go. Let's do an integral. So go to Math 9 to bring up your integral. You guys probably have the one that looks better. Mine's the ugly one. The first thing you type in is your function that you're integrating. So that's 180 plus 3t. X in this case is fine. Comma. Then we're going to tell our calculator what variable we're integrating with respect to. And then we're going to tell our calculator what intervals we're looking at from 0 to 20. And then we push enter, and it's 4,200.
Oh.
So that means after 20 minutes have gone by, 4,200, well, 4,200 something. Let's figure that out though. What are the units for h of t? It's liters per minute, right? And this is dt. What does that represent? Minutes. It's time. What's liters per minute? What's liters per minute times minute?
Years. Oh my God.
So that's how many liters that we had the O moment. There it is. That's good. That means that after 20 minutes, 4,200 liters have flowed into that tank. Okay? So if you integrate a rate, you get the total amount that occurred over that time period. That's the big takeaway for today. All right. If there was initially 500 liters in the tank, how much will there be after 20 minutes? You know, that's confusing wording. Let me change this, because that caught somebody in my So if let's say the tank started with 500 liters in it to begin with, before they started putting any chemical in there at all, how much will there be after 20 minutes gone by, like at that 20-minute mark? Yeah, 4,700, right? You take the starting amount and you add it to the net change. Now I'm gonna write it in a much uglier way, but I want it to be that common sensey. But let me show it to you. So I want to know my final amount, right? The final amount we saw on the last slide is equal to the starting amount plus the net change, right?
Yeah.
I'm putting F. What should I be putting here? Big H, right? There we go. And what am I going to put in for X? So X is my, yes, it's my final time. So H of 20 is equal to H of A. What's my A? My starting time, or my starting amount, plus 0 to 20 of my function, right? Now we already figured some of this stuff out here. H of 20 is equal to, what's H of 0? Now a big H represents, yeah, how much you started with, the starting amount, right? Remember on the last slide I labeled the big F of A as your starting amount? So big H of 0 is my starting amount. That's 500 liters is what we're starting with. And what did we calculate the net change to be?
4,200.
Which means that the final amount, the amount of chemical after 20 minutes, is what Jacob already knew in advance, because it was just, I wanted it to seem obvious, but I'm showing you the calculus approach, like how you would show your work for that. So final amount is equal to starting amount plus the net change. Final amount, starting amount, net change. That's your answer, right? So part C asked us to write an integral function that represents the amount of chemical in the tank at any time, so that means that instead of finding a specific value for X, we're just going to leave X in there. Okay, so H of X is equal to your starting amount. So for this particular problem, what's my starting amount? 500. Now you could put a big H of 0 if you want to, but we want to put it in the simplest form we can. It's just easier to put 500 there. And then plus what's my integral going to be from 0 to what? X, right? Because it's a function for any time now. And then it's going to be h of t dt. So now we have an integral function that represents how much chemical will be in the tank after any given time period. So the amount of chemical in the tank at any given time period, x, will always be 500, starting amount, plus the integral of your rate from 0 to whatever time period you're looking at. Okay? So a lot of the math we're doing, like I said, is not new. It's just interpreting it in the word problem. So here's one for you guys. Go ahead and see what you can do with it.